Good morning. My name is Icaro. I'm from the ITR in France, and I will present about the electromagnetic assessment of the electromagnetic exposure assessment of bioelectronic wireless charging of bioimplantable devices. So let's start with a quick overview of bioelectronic implants. Today, these kind of devices bring new possibilities in medicine. For instance, we can use for get more robust and precise diagnostics and also less invasive treatments. As an example of some applications, in biotelemetry, you can use to analyze endoscopic data to get pH values, temperature, glucose. But also in electroceuticals, in this new field, we can use to improve people's life by having a new kinds of treatments for neural disease. And with this, like have a less invasive treatment. But one problem we have One problem we have here with this kind of devices are the batteries. Why? Okay, the batteries is the most space-consuming component for these bioimplants. And apart from that, the lifetime of batteries are very short. So for each recharging or replacing the batteries is a new surgery. It's more invasive. And also it reduces the possibility of applications. Once the batteries take so much space, we can only, the power budget is limited, we can today apply just in simple applications. If we have like a solution to remove these batteries or to recharge them, we can pave the way for more breaking through applications, for example. So, okay, thank you. So what is the solution for this problem? Wireless power transfer. Here, in applying wireless power transfer, we can solve most of these problems and reduce the usage of these batteries and how to recharge them. But for the challenge here is the application of these wireless power transfer techniques that we have in free space are much more complex in the human tissue because they are like a dispersive medium, and most important, we have the user safety to be worried about. How we can like transfer energy inside the body, but also ensure minimum SAR, ensure the user safety. Here, just to have an overview of the main techniques applied for bioimplants. For subcutaneous applications, where the distance between the transmitter and receiver are very short, we can apply magnetic coupling, magnetic wireless power transmission. It leads to highest efficiency. But as we go deeper in the body, today, the most applied techniques are the mid-field and far-field applications. Here, we also include the ultrasonic, even though this technique can be applied for any implantation depth. As we can have more control from the, wave control, here we can focus in more deep implanted devices as well. So, once we have our problem, how we can formulate to solve them? So, we start here by taking the example, by taking as a case study, the deep implanted pacemaker proposed by John Hu. Here we have like a photo for this pacemaker, is very, very tiny, and it is implanted directly in the heart. So for this, we consider a 2D cross-section for the human pectoral. And as we assume that the transmitter and the receiver are perfectly aligned, we can also assume the invariance in the z-axis. This reduces a lot of the computational cost of this problem. And we consider here 8 different tissues with frequency-dependent characteristics. And here, the geometry for our pacemaker or receiver is this yellow bubble in the heart, is the same as the one built by John Hu here, proposed by him. So, how to model the transmitter? The transmitter is considered close to the scheme, and it's composed by 3 parts. First, we have this buffer. that's a dielectric with the characteristics similar to the body. We can compare this with the gel used in ultrasound. So with this, we can reduce the reflection losses from the transmitter to the body. And then we have our source and our air substrate. But how to model the source? We consider here two different kinds, an electric and a magnetic one. For the electric one, we model as a line current distribution, where we can see in the second figure, a line current distribution similar to a dipole antenna, for example. And here in the blue arrows, we have the electric field generated by this current distribution. As we can see, the field is more concentrated in this case, in the middle. It will be important for us. And also we can model the magnetic source as a loop antenna, as out-of-plane current with unitary values. And here the field is more concentrated around the edges of these wires. So once we have our problem, the geometry formulated, we can solve numerically. First, we simulated this problem as a 2D simulation in console. And from this, we can get the electric and magnetic fields. Based on these fields, we can find and considering the energy conservation, we can say that the transmitted power is the integral of the power flow over the transmitter surface. For the receiver, is the same integral of the power flow, but in the receiver surface, in the yellow bubble. And to get the power dissipated in the body, we can integrate the losses over the entire body area. And based on these three values, we can calculate the three parameters we use in our analysis. The absorbed power as a ratio of the dissipated power and the transmitted, the efficiency as a ratio between the received and the transmitted power, and the SAR we use to calculate the electromagnetic exposure. So here we have our results. Let's start by the electric source. In this first graph, for all the three analyses, we consider the frequency range from 100 megahertz to 5 gigahertz. And in the first one, we have the SAR normalized by the transmitted power. As you can see, the electric source presents a high SAR in lower frequencies, and it reduces for higher frequencies, reaching the minimum around 890 megahertz. Then we have the absorbed power here in the second graph. And as we can see, the absorbed power it decreases over the frequency, except by this frequency in 1.86 gigahertz. This is due to resonance modes that lead to this high absorption. And finally, we have the wireless power transfer efficiency here. And as we can see for the electric source, the maximum is reached between 700 and 2 gigahertz. This results agrees with our previous results on physical bounds on the wireless power transfer efficiency for implantable devices. And now the same results for the magnetic source. As you can see, the magnetic source for lower frequencies presents a much low SAR. However, it increases with the frequency. It's the same region where the efficiency increases. For the absorbed power, we can see for the magnetic source, it's almost constant over the entire frequency band, except for the very high frequency, and it's much higher also than the electric source. And finally, in this case, the magnetic source proves to be suboptimal, with very low efficiency compared with the electric source. This is due to the fact the magnetic source acts better as an electrically small antenna, which is not the case in your study. That leads to a very low efficiency. But also, we can, based on these graphs, we can find the best operation conditions for this kind of application, for charging a pacemaker, a deep implanted pacemaker. We can see that around 891.2 megahertz, we have the minimum SAR, we have a low absorbed power, and also we have an efficiency very close to the maximum one. So in this case, we have best of both worlds. We have best efficiency, at the same time we have very low exposure. And finally, we can compare here the local SAR for different frequencies. As we can see for the electric source, in 891.2 megahertz is the lowest SAR we can get. And as we saw in the field distribution, for the electric source, this, as it follows the field behavior, so the SAR is more concentrated in the middle, whereas for the loop antenna, the magnetic source is more concentrated around the loop edges. And also, it's important to see the SAR, the highest SAR is concentrated in the skin. In any vital organ is affected by high exposure levels. So with this slide, I want to conclude with the short summary. I want to conclude this presentation. So what we show here, wireless power transfer can bring many benefits to bioelectronic implants, to get better treatments and to get much more advanced applications. However, exposure assessment is very important in this kind of application as well. It also, finally, we present, we can also have good efficiency and very low exposure. In this way, you can please like the engineers and also the regulatory agencies. You can ask him, I'm very happy to answer any question here or by email. Thank you very much.
Thank you, Icaro. Are there any questions in the room? Okay, Michaela.
Thank you, Michaela Liberti again. Today I'm very interested in this. No, very interesting approach, but I lost some points. First of all, is your model to bidimensional or three-dimensional? And the other point is that you kept the source always the same, but there you have a strong near-field interaction. So I think that what you can really measure in terms of SAR greatly depends on the source, on the model. So if the model is not three-dimensional, the approach is interesting and valid, but the results interpretation maybe is not as much reliable for a real use. Mm-hmm. Thank you.
Thank you for the question. Yes, we use a 2D model for this analysis. It's for this kind of application, once we want to see the maximum possible efficiency, but also the maximum SAR, we believe that the 2D model is a good strategy for first analysis. Once, as we saw, the SAR is the highest SAR region is very close, it's located very close to the source. And as the body is very dispersive, for distance very far from the source, the field will be almost entirely attenuated. So here, this 2D model, even though we do lots of assumptions, it is our best case scenario, we can say. So with this, we can assume that the maximum SAR we could get, because in a physical, in a realizable problem, in experiment, it will be much lower than this one. This is the maximum we can get.
Okay, we have another question in the chat. The question was whether the sources that you use are based on real devices and whether they are realistic or not. Both sources represent antennas, conventional antennas. For the electric source, we use the same field distribution as a dipole antenna. And for the magnetic source, we use the same as a loop antenna. So with this, we can have a good analysis of the main kinds of antennas used for a transmitter, for example, the simplest one. Okay, thanks. Are there any other questions? Yes.
Thank you. My question was actually quite similar to the one in the chat. Like, how did you decide the geometry of the charger or the antenna, and how I noticed that you defined it by the permittivity. What if you change the permittivity of the buffer and the substrate? Did you actually optimize this?
Yes. Thank you for the question. Yes, it's one thing we are working now. This idea here, I'll come back for the slide for the transmitter, just a minute. Here, the next one. Yes.
The receiver, the size for the receiver was based on John. It's like the same size for his pacemaker. For the transmitter here, we use this buffer also to reduce the reflection losses. But by further studies we are doing now, carrying out now, we can see we can optimize the distance and the permittivity for the buffer in order to increase even more the efficiency and reduce SAR. So we can go even beyond that. So the buffer is a way we can use to improve both performance and reduce the exposure as well.